यस, वेलकम ऑल ऑफ यू। जैसा कि फर्स्ट लेक्चर में हमने बताया था, मोशन इन प्लेन ये चैप्टर जो है वो एक्चुअली 3 पार्ट्स में बटा हुआ है, जिसमें से फर्स्ट पार्ट जो है तो वो है बेसिक्स ऑफ काइनेमेटिक्स, जिसके अंदर इन जनरल काइनेमेटिक्स के अंदर जो मींस इन जनरल मोशन जो होता है, तो मोशन के बारे में हमने स्टडी किया। तो उसमें जो 3 कंसेप्ट होते हैं, जैसे कि डिस्प्लेसमेंट, वेलोसिटी और एक्सेलरेशन, इन तीनों के बारे में हमने स्टडी किया, उनके डेफिनेशंस, और इवन उससे भी आगे जाके उनके जो इंटररिलेशनशिप्स, मतलब डिस्प्लेसमेंट, वेलोसिटी और एक्सेलरेशन, इन तीनों के बीच में क्या रिलेशनशिप्स है, तो वो सब भी हमने ऑलरेडी देखा। और सेकेंड पार्ट जो है इस चैप्टर के अंदर का, तो वो है प्रोजेक्टाइल मोशन। ठीक है ना। तो प्रोजेक्टाइल मोशन के अंदर हमने स्पेशली प्रोजेक्टाइल मोशन के ऊपर फोकस किया, जो कि कल ही हमने वो एक्चुअली खत्म किया। तो उसके अंदर हमने देखा कि प्रोजेक्टाइल मोशन विच इज अ स्पेशल टाइप ऑफ प्लेनर मोशन और मोशन इन प्लेन, तो उसके बारे में, उसके अंदर जो रेंज, मैक्सिमम हाइट, टाइम ऑफ फ्लाइट एंड ट्रेजेक्टरी, और उनके अंदर के जो इंटररिलेशनशिप्स है, तो उसको यूज करके किस तरह से न्यूमेरिकल्स और एमसीक्यू सॉल्व करने का, तो वो सब हमने देखा लास्ट लेक्चर में। अभी जैसे कि उसका थर्ड पार्ट जो बचता है, मोशन इन प्लेन का थर्ड पार्ट, वो है सर्कुलर मोशन, यूनिफॉर्म सर्कुलर मोशन। दैट इज वी हैव टू डिस्कस इन टुडेज लेक्चर। So first of all, we will try to understand the theory and some shortcuts, and then we'll go to the MCQs. Actually, let us start. Yes. I hope you can see the slides. So basically, वैसे तो ये टॉपिक जो है वो सीबीएसई बोर्ड के हिसाब से अगर देखा जाए, तो सिस्टम ऑफ पार्टिकल्स एंड रोटेशनल मोशन इस चैप्टर के अंदर आता है। तो लेट अस सी द इंट्रोडक्शन ऑफ सर्कुलर मोशन। व्हाट इज सर्कुलर मोशन? वी नो ऑलरेडी दैट it is the motion of the particle performing, or motion of the particle along the circumference of any circle is called as the circular motion. And circular motion, अभी जैसे कि हम जानते हैं कि motion is of categorized in different types, like translatory motion means एक straight line में जाने वाला motion, दूसरा है oscillatory to and fro motion, और तीसरा टाइप में जो हम देख सकते हैं, it is a circular motion. So in case of the translatory motion, the particle has the same velocity. ठीक है। तो इस केस में हम देख सकते हैं आराम से कि ट्रांसलेटरी मोशन के अंदर क्या होता है, पार्टिकल का जो वेलोसिटी है वो कांस्टेंट होता है। ठीक है ना। उसका डायरेक्शन जो है वो बदलता नहीं है, डायरेक्शन डजंट चेंज, डायरेक्शन रिमेन्स द सेम। द पार्टिकल विल मूव इन अ स्ट्रेट लाइन, that is called as a translatory motion. In case of the oscillatory motion, as we can see it in the diagram, the motion will be periodic, and it will, the velocity, direction of velocity will change after certain equal intervals of time, and that's why it's called as the oscillatory motion. Okay. But the circular motion is a special category of motion in which the particle revolves along the circumference of a circle. That is actually called as the circular motion. Just like we can see, the particle is revolving in the circular motion in along the circumference of the circle, and it has many examples. Like we can see motion of the earth along the sun, or motion of moon along the earth, or motion of electron around the nucleus. All these are the circular motion. But when we come to the circular motion, there are two categories of circular motion. One is called uniform circular motion, and another one is called as the non-uniform circular motion. When we talk about the uniform circular motion, ठीक है ना, उसको हम यूसीएम से भी डिनोट करते हैं, यूसीएम। ठीक है। और दूसरा जो है वो नॉन यूसीएम से उसको डिनोट कर सकते हैं। What is the basic difference between this UCM and non-UCM is, in case of the UCM, we can see clearly the particle, motion of the particle along the circumference of the circle with the constant speed. Okay, constant speed मतलब क्या? यहाँ पे speed is going to be the constant. Speed is not going to change. तो तो स्पीड जो है वो चेंज नहीं होना चाहिए, हर पॉइंट पे पार्टिकल का जो स्पीड है वो कांस्टेंट होता है, उसको हम बोलते हैं यूनिफॉर्म सर्कुलर मोशन। सी so far as the revolution of moon is concerned around the earth, we can see that it requires the same time to complete a circle, every circle। तो हर सर्कल को कंप्लीट करने के लिए जरूर उसको सेम टाइम लगता है। इवन मोशन ऑफ अर्थ अराउंड द सन is also the special type of uniform circular motion because it takes the same time every time। If suppose first circle is completed in some another time and second circle takes to complete another time, in that case we can say that it will not be a uniform circular motion but it will be a non-uniform one। okay, तो ये सब हम समझ सकते हैं। In case of non-uniform circular motion, the speed is variable। okay, variable speed, the definition is almost the same। see, the motion of the particle along the circumference of the circle with variable speed, that is the important thing to understand here। the speed is variable। when we talk about the giant wheel, it goes on starting, when it starts, we can see the speed of every particle goes on increasing continuously unless and until it attains the full value, and then again goes on decreasing when it stops finally and it becomes zero। so this is the example of non-uniform circular motion। even fan, when the fan is switched on, what happens is its speed goes on increasing continuously, and so far as its speed is changing, we can say that the motion is called non-uniform circular motion। no doubt, once its speed becomes constant, we can call it as a uniform circular motion। but when the speed goes on decreasing once again, when the speed starts decreasing once again, then in that case we can call it as a non-uniform circular motion। तो जब जब स्पीड चेंज होता है तब तब वो नॉन यूनिफॉर्म सर्कुलर मोशन है, जब जब स्पीड कांस्टेंट रहता है तब तब वो यूनिफॉर्म सर्कुलर मोशन है। इवन जायंट व्हील का भी वैसे ही है, जायंट व्हील का भी ऐसे ही, ऐसे नहीं कि जायंट व्हील हमेशा नॉन यूनिफॉर्म सर्कुलर मोशन परफॉर्म करता है, नहीं, only it when it starts and when it stops it performs non-uniform circular motion। but when it is rotating with a constant speed, in that case we can say that giant wheel also is performing the uniform circular motion, no doubt। okay, just check your understanding। the motion of the particle along circumference of a circle with constant speed is called as, just put it in chat box fast, motion of particle along circumference of a circle with constant speed, what is it called? Uniform circular motion। A is going to be the correct option, right? yes, okay, just take the options only, number option का number type करने में थोड़ा कम समय लगेगा। yes, चलो next one। the motion of particle along the circumference of a circle with changing speed is called, yes, simply we can say it will be B, that is non-uniform circular motion। very good, Aditya। yes, the motion of an object along the straight line, what is it called? straight line में अगर वो जाता है तो उसको क्या कहेंगे? linear motion। okay, C will be the correct option। okay, चलो ठीक है, now we'll understand the concept of radius vector। what do you mean by this radius vector? it is denoted by r bar। in case of the circular motion, the vector drawn from the center of the circle to the position of the particle is also called as the radius vector। as we can see here, in this case, if we draw, if the particle is present at this point here, that is located by green circle, ये green circle जहाँ पे है वहां पे अगर particle located है तो हम radius vector कैसे draw करेंगे? तो देखो ये हो गया उसका radius vector, उसको हम बोलेंगे r bar और r1 bar we can say। when the particle will move along the circle and be located at this another point at point P2 suppose, then the radius vector will just get changed and that will be called as the R2 bar at that time। so this is the radius vector R2 bar which is different from R1 bar। you can see clearly as the particle goes on moving from one point to another point on the circle, the radius vector goes on changing, not in magnitude, only in direction। तो डायरेक्शन के अंदर ये रेडियस वेक्टर जो है वो कंटिन्यूअसली चेंज होता जाता है, ये हम समझ सकते हैं आराम से। ओके, इवन व्हेन इट गोस टू द थर्ड पॉइंट, सपोज P3, In that case, the radius vector will again change and it will be called as r3 bar, and so on like that. So accordingly, radius vector, when the uh, particle moves along the circle, the radius vector has constant magnitude, and that constant magnitude of radius vector is also called as the radius, only radius, and it is always denoted by r, remember. But this we have to say that this r1 bar, r2 bar and r3 bar are not going to be the same just because of direction. Their directions are different, and that's why r1 bar is not equal to r2 bar and it is not equal to r3 bar. ये equal to क्यों नहीं है? क्योंकि direction की वजह से, याद रखो ठीक से. And it is also called as the position vector, ठीक है ना, because it is joining the origin and the position of the particle also. And its SI unit is meter and its dimensions are m1 m0 l1 t0, no doubt. चलो अभी रेडियस वेक्टर के बारे में बताओ फटाफट. डायमेंशंस ऑफ रेडियस वेक्टर इज गिवन बाय, ये देखो बी सी आंसर उसका करेक्ट होगा, m0 l1 t0 करेक्ट है. जस्ट अभी अभी हमने देखा था. देखो सपोज रेडियस वेक्टर इज आल्सो कॉल्ड एज पोजीशन वेक्टर, राइट? यस. नाउ we'll see the concept of angular displacement. What do you know the angular displacement is? See, the angle traced by a radius vector in a given time. Suppose the particle is at the point A here. तो अगर पार्टिकल A पॉइंट पे है सपोज, ठीक है, और अगर मान लो कि वो A से दूसरे पॉइंट पे चला जाता है B पॉइंट पे, तो अभी देखो रेडियस वेक्टर ने कितना एंगल कवर किया, तो ये इतना एंगल कवर किया, देखो थीटा इतना एंगल उसने कवर किया. So this angle covered by this radius vector is actually called as the angular displacement, and this angle always is measured in radian, remember. And as we know that this angle in radian theta is defined to be equal to arc s upon radius r. So this, therefore we can say that this s is going to be equal to r into theta, where r is going to be the radius and theta is going to be the angular displacement. So this is the relationship between angular displacement and arc length here, remember this correctly. And even for if suppose this angular displacement is very small, then in that case the this linear displacement, ये जो arc length है, तो ये arc length जो है वो हम almost straight consider कर सकते हैं. It can be considered to be almost straight, and in that case we can put this in a vector form. तो इस केस में हम यहाँ पे जो है ये डेल्टा s जो है तो वो r into डेल्टा थीटा ऐसा लिख सकते हैं. देखो this is the equation, relationship between delta s and delta theta, which is also obtained from the same formula, that is angle is equal to arc upon radius. ये बेसिक फॉर्मूला है एंगल का. इन रेडियन में ये इस तरह से डिफाइन किया जाता है एंगल. तो अगर हम ये यूज करेंगे यहाँ पे, तो ये जो छोटा वाला एंगल है डेल्टा थीटा उसको हम बोल रहे हैं. The delta theta will actually be equal to arc in front of that angle, which is going to be delta s here. So delta s, and that is to be divided by r. And if we take this r in that side, then we can get this as delta s is equal to r into delta theta as the final equation, or relationship between this infinitesimal, this small angular displacement, and infinitesimal small this linear displacement or arc length we can say. And this equation can be put in the vector form like this. See here, this is the vector form of this equation. What does it tells us? That delta s bar is going to be the cross product of delta theta bar and r bar, as we already have seen it in the theory also. When we have discussed the chapter, we have already seen this concept as it is. So delta s bar is equal to delta theta bar cross r bar. This is the vector product actually. Okay. So next is about the SI unit of this angular displacement is going to be the radian, and its dimensions are 0, 0, 0. That means it is dimensionless, and its direction is given by right hand thumb rule. See here, right hand thumb rule क्या बताता है हमको? If suppose the particle is revolving along the circle in this way, in the anticlockwise direction, then we can turn the fingers of our right hand along the sense of rotation, and whatever the direction thumb is denoting will be called as the direction of angular displacement, like this. If we take our right hand and turn our fingers of right hand along the direction of rotation, then whatever direction thumbs point it out is called as the direction of angular displacement, which is always going to be perpendicular to the plane of circle. तो जिस प्लेन में सर्कुलर मोशन हो रहा है, उस सर्कल को परपेंडिकुलर डायरेक्शन में ये पार्टिकल का एंगुलर डिस्प्लेसमेंट कहलाता है. This vector delta theta bar will be the vector which is called as the angular displacement vector. Remember. ओके अभी देखो, अगर ये पार्टिकल अगर इस डायरेक्शन में अगर ऐसा घूम रहा है, तो उस केस में हम देखेंगे कि इसका एंगुलर डिस्प्लेसमेंट ऊपर के डायरेक्शन में आएगा, नो डाउट. लेकिन अगर पार्टिकल उल्टा घूमता है बाय चांस, तो उस केस में क्या होगा, एंगुलर डिस्प्लेसमेंट डाउनवर्ड डायरेक्शन में आएगा. तो इसका मतलब अगर एंगुलर डिस्प्लेसमेंट इस डायरेक्शन में है, दैट व्हाट डज इट मीन, द पार्टिकल मस्ट बी रोटेटिंग लाइक दिस. इफ द एंगुलर डिस्प्लेसमेंट इज गोइंग टू बी दिस डायरेक्शन हियर, दैट मीन्स द पार्टिकल मस्ट बी रोटेटिंग लाइक दिस, इन दिस वे. सो जिस डायरेक्शन में भी एंगुलर डिस्प्लेसमेंट होगा, तो उसके हिसाब से एंगल जो है, तो जो एंगुलर डिस्प्लेसमेंट का जो डायरेक्शन है, तो वो हमेशा उसको परपेंडिकुलर होगा. तो एंगुलर डिस्प्लेसमेंट के डायरेक्शन से हमको क्या पता चलता है, सेंस ऑफ रोटेशन, what plane the particle is rotating and in which direction, clockwise or anti-clockwise, that is understood from the concept of angular displacement. See here in this picture we can see that if the particle is rotating in the clockwise direction, then the angular displacement will be downwards. But on the other hand, if suppose the particle is moving in the anti-clockwise direction, then the angular displacement will be in the upward direction. तो जैसा अभी पिछले स्लाइड में हमने जो देखा था ना, तो उसमें हमने देखा था कि particle will be moving in the anti-clockwise direction as seen from the top. So therefore, if we turn the fingers of right hand along the sense of rotation, then thumb will automatically point in the upward direction. But if suppose in this case the particle is rotating in the clockwise direction, and in that case if we turn our fingers of right hand in the in the direction of sense of rotation, then automatically thumb gives us in the downward direction. The thumb points in the downward direction, and that's why we can call it as a direction of angular displacement. Now just check your understanding. Direction of angular displacement is given by which rule? देखो राइट हैंड रूल भी अलग अलग होते हैं. राइट हैंड पाम रूल भी होता है, राइट हैंड स्क्रू रूल भी होता है, राइट हैंड थंब रूल भी होता है. बट बेसिकली all these three are going to be the same only. तीनों का मतलब एक ही है. स्क्रू रूल का भी मतलब वही होता है. स्क्रू जब हम फिट करते हैं, ऐसे टाइट करते हैं, तो उसकी वजह से स्क्रू अंदर जाता है. बराबर, देखो इस तरह से अगर हम टाइट करते हैं तो स्क्रू अंदर जाता है, और जब लूज करते हैं, उल्टा उसको घुमाते हैं ऐसे, तो वो बाहर आता है. तो इट इज वन एंड द सेम थिंग. So all of these three rules mean the same thing, no doubt. Next is for a circular motion, the angular displacement is the angle traced by radius vector in a finite time. Okay, radius vector के द्वारा finite time के अंदर जो angular displacement होता है, उसको हम बोलते हैं angular displacement. Remember. The next is unit of angular displacement is. What is the SI unit of angular displacement? Type in the chat box fast. Angular displacement का यूनिट क्या होता है? Yes, it is radian. Okay, that is C is going to be the correct option. Yes. What are the dimensions of angular displacement? Already अभी हमने देखा. What are the dimensions of angular displacement? Yes, type in the chat box fast. Dimensions of angular displacement. Already we have seen just now that the angular displacement is dimensionless. Okay, angular velocity, that is the next concept in this chapter here. So you will see the time rate of change of angular displacement is called as the angular velocity. Suppose the particle is moving along the circle, and suppose it is moving from point A to the point B in time t. Then we can see theta1 is the angle traced by this radius vector, that is angular displacement here. Then we can just take the ratio of theta1 to t1. ठीक है, सपोज ये जो रेशियो है, ओके, सपोज ये बी से सी तक टी इतने टाइम के अंदर वो चला जाता है, तो उस केस में हम क्या करेंगे, यहाँ पे देखो थीटा वन, सॉरी, ये थीटा वन पे जब वो आता है, मतलब बी पॉइंट पे जब आता है, तो उस समय का टाइम इंटरवल इंस्टेंट t1 था सपोज, और जब सी पे आता है तो उस समय का टाइम इंस्टेंट t2 था सपोज, ठीक है। तो यहाँ पे बी से सी तक जाने के लिए उसको कितना टाइम लगा, तो उसको हम बोल सकते हैं t2 माइनस t1, इतना टाइम लग रहा है, राइट। और बी से सी तक जाने के दौरान उसने कितना एंगल कवर किया, तो देखो स्टार्टिंग में ऑलरेडी उसने थीटा वन इतना एंगल कवर करके रखा था, और उसके बाद स्टार्टिंग से अगर मेजर किया जाए तो थीटा टू इतना एंगल उसने कवर किया सी तक जाने के टाइम तक, तो इसलिए थीटा टू में से थीटा वन हमको सबट्रैक्ट करना पड़ेगा, जिससे हमको मिलेगा थीटा टू माइनस थीटा वन, which is also denoted by delta theta, and that is to be divided by delta t, which is going to be actually the angular velocity, which is nothing but the rate of change of angular displacement, or we can also call it as a, or say it as a ratio of angular displacement to the angular time interval. Time interval for that is also called as the angular velocity. But this is nothing but the average angular velocity. Why it is average? Because we have taken it over the interval, some interval, कुछ interval के ऊपर हमने उसको निकाला है, and it's a vector quantity, and its direction is again be the same as the angular displacement. जैसा भी हमने देखा कि एंगुलर डिस्प्लेसमेंट का डायरेक्शन जैसे राइट हैंड रूल से दिया जाता है, सेम वैसे ही हमको यहाँ पे एंगुलर वेलोसिटी का भी डायरेक्शन निकालना होता है, बट इसका यूनिट हमको याद रखना है ठीक से, इट्स यूनिट इज गोइंग टू बी रेडियन पर सेकेंड, एंड डायमेंशंस विल बी ऑब्वियसली m0, l0 and t-1, ओके। एंड इंस्टेंटेनियस एंगुलर वेलोसिटी के लिए हमको क्या करना पड़ेगा, the instantaneous angular velocity can be defined as the limiting ratio or limiting rate of change of angular displacement with respect to time. So rate of change of angular displacement with respect to time, which is called as a instantaneous angular velocity, which is obtained by delta theta by delta t, and this limit of this ratio as delta t tends to 0. This is called as the angular velocity, instantaneous one. And it is also found out to be d theta by dt. That means the derivative of theta with respect to time. Remember. Now we'll talk about the angular acceleration, which is the rate of change of angular velocity with respect to time. Suppose that there is a particle which turns from or travels from A to B, and suppose that at point B it has its angular velocity omega 1, okay. And suppose at point C here its angular velocity is going to be omega 2, and this change takes place in time t suppose. Then we can see what is the change in angular velocity when traveling from omega 1 to omega 2. तो उसका इनिशियल एंगुलर वेलोसिटी कितना था, ओमेगा 1 था, और उसका फाइनल एंगुलर वेलोसिटी कितना बन गया, ओमेगा 2. So what is the change in angular velocity? We can see the change in angular velocity is to be found out by the ratio of say difference of omega 2 and omega 1. So this is omega 2 minus omega 1. It is called as the change in angular velocity, and that change is to be divided by time, which gives us the angular acceleration, which is denoted by alpha. Remember, and obviously from this formula itself we can find out the unit of SI unit of this angular acceleration, which is going to be radian per second square. Remember. And dimensions, obviously it will be m0, l0, t-2, because omega doesn't have any dimensions, right? So t has dimensions, that is t1. Sorry, the omega has a dimensions of t-1, right? And यहाँ पे नीचे t1 है, तो वो ऊपर जाके बनेगा t-1, and hence t-1 becomes t-2. So these are the dimensions of angular acceleration. And if we want to talk about the instantaneous angular acceleration here, then we can say in a very small amount of time, delta t, the angular velocity changes by suppose delta omega. Then we can say this delta omega by delta t, and the limit of this ratio as delta t tends to 0 is called as the instantaneous angular velocity, which is nothing but the derivative of omega with respect to time, d omega by dt, you can say. The next is again direction of angular velocity and angular acceleration. एंगुलर वेलोसिटी का जो डायरेक्शन है वो तो हमने ऑलरेडी देखा कि वो एंगुलर डिस्प्लेसमेंट के डायरेक्शन में ही होता है, एंड इट इज आल्सो ऑलवेज गिवन बाय राइट हैंड थंब रूल और राइट हैंड palm rule और राइट हैंड स्क्रू रूल, नो डाउट. बट अल्फा का जो डायरेक्शन है तो वो इसके ऊपर डिपेंड करता है कि वेदर द एंगुलर वेलोसिटी ओमेगा इज इंक्रीजिंग और डिक्रीजिंग. देखो ठीक से, ये बहुत इंपॉर्टेंट बात है समझने जैसी. हाउ टू फाइंड द डायरेक्शन ऑफ एंगुलर एक्सेलरेशन अल्फा हियर. So if angular velocity omega bar is increasing with time, then in that case alpha is in the same direction as that of omega. Okay, मतलब अगर ओमेगा बार जो है वो टाइम के हिसाब से बढ़ रहा है तो ऐसे केस में अल्फा बार का जो डायरेक्शन है तो वो एग्जैक्टली ओमेगा बार के डायरेक्शन के सेम ही होता है, पैरेलल ही होता है, नो डाउट. फॉर एग्जांपल, इफ सपोज पार्टिकल इज like this, increasing the angular velocity in this case, then in that case we can say that angular velocity and angular acceleration are in the same direction, no doubt. But in case when omega bar is decreasing with time, okay, suppose अगर omega bar जो है मतलब angular velocity जो है तो वो अगर decrease हो रहा है, if the particle is slowing down, then in that case the direction of alpha bar is opposite to डायरेक्शन ऑफ ओमेगा बार. ओके, तो मतलब जब एंगुलर वेलोसिटी डिक्रीज हो रहा होता है तो उस केस में क्या होता है, अल्फा बार का जो डायरेक्शन है, एंगुलर एक्सेलरेशन का जो डायरेक्शन है वो एंगुलर वेलोसिटी के डायरेक्शन के अपोजिट में मिलता है. देखो अगर ये पार्टिकल स्लो डाउन हो रहा है, दिखना ठीक से, इफ द पार्टिकल इज स्लोइंग डाउन then in that case angular velocity will be still in the upward direction, no doubt. But in that case the alpha bar, that is the angular acceleration vector, will be directed in the direct downward direction, which is opposite to this omega bar here. Omega bar is in the upward direction, but alpha bar is going to be in the downward direction because omega is decreasing. Okay, omega decrease होने की वजह से alpha bar का डायरेक्शन omega bar के opposite में मिलता है, और ओमेगा के इंक्रीज होने की वजह से अल्फा बार का डायरेक्शन ओमेगा बार के डायरेक्शन के सेम डायरेक्शन में मिलता है. ये बात अच्छी तरह से याद रखो. Okay, there are three equations of motion in rotational motion also. मतलब यहाँ पे काइनेमेटिक्स के जैसे हमारे पास जो तीन इक्वेशंस थे जो कि v इक्वल टू u प्लस at, एंड ये देखो v इज इक्वल टू u प्लस at, ये हमारा फर्स्ट काइनेमेटिक इक्वेशंस था. तो यहाँ पे v किससे रिप्लेस हो गया, ओमेगा से. u किससे रिप्लेस हो गया, ओमेगा नॉट से. और a किससे रिप्लेस हो गया, अल्फा से. व्हाट इज दिस ओमेगा नॉट कॉल्ड, इट इज कॉल्ड एज इनिशियल एंगुलर वेलोसिटी. Remember, okay, it's called as the initial angular velocity. ये देखो यहाँ पे initial angular velocity is called as omega naught, and final angular velocity is denoted by omega only. This omega is going to be the final angular velocity, and the angular acceleration here is denoted by alpha, and time तो time ही होता है, ठीक है नहीं. तो इसलिए omega is equal to omega naught plus alpha t. This is the very similar equation with the first kinematic equation in motion, planar motion. Okay, तो जो हमारा फर्स्ट काइनेमेटिक इक्वेशन होता है वैसे ही सर्कुलर मोशन के अंदर भी फर्स्ट काइनेमेटिक इक्वेशन है. जैसा कि हम जानते हैं इन प्लेनर मोशन देयर इज अ सेकंड काइनेमेटिक इक्वेशन व्हिच इज डिनोटेड बाय s इज इक्वल टू ut प्लस हाफ a t स्क्वायर. करेक्ट है. सो यहाँ पे s के बदले क्या आ जाएगा, थीटा. देखो ठीक से, क्योंकि s इज कॉल्ड एज अ लीनियर डिस्प्लेसमेंट, बट दिस थीटा इज कॉल्ड एज द एंगुलर डिस्प्लेसमेंट. ओके, तो दिस इज रिप्लेस्ड हियर, एंड u के बदले क्या आने वाला है, ओमेगा नॉट. u is called as initial velocity, omega naught is going to be the initial angular velocity, and a के बदले क्या आने वाला है, अल्फा. a is called as acceleration and alpha is called as angular acceleration. And this third kinematic equation which will say that v square is equal to u square plus 2as. So here v is replaced by omega, u is replaced by omega naught, and a is replaced by alpha, and s is replaced by theta as usual. And this is called as actually the third kinematic equation of motion in case of circular motion. Okay, now just check your understanding. The angular acceleration is given by, yes, just type in the chat box what is the formula for angular acceleration. Instantaneous, obviously. What is the correct answer? See, what is the basic difference between all this formula is here bar is missing, right? Here again bar is missing. So we can say that alpha bar is equal to d omega bar by dt. That is, A is going to be actually the correct option. Just check. Time rate of angular displacement is called angular velocity. Remember. Yes, dimensions of angular velocity. Who can type in the chat box fast? What are the dimensions of angular velocity? अभी देखा हमने angular velocity के dimensions क्या होते हैं? Yes, t minus 1. Very good. C is correct option. Correct. चलो ठीक है, तो अभी हम देखेंगे यूनिफॉर्म सर्कुलर मोशन. यस, रिलेशनशिप बिटवीन द लीनियर स्पीड एंड एंगुलर स्पीड, मतलब v और ओमेगा, इन दोनों के बीच में जो रिलेशनशिप होता है वो है v is equal to r omega. So consider a particle which is performing uniform circular motion along the circumference of a circle of radius r and center at O. Then its linear speed will be the if suppose in a small time interval it get displaced by an amount delta s. This is the linear displacement of the particle, and delta theta is going to be the angular displacement of this particle. Now already we have proved that delta s is equal to r into delta theta. If we just divide the both sides by delta t and just take the limit as delta t tends to 0, then the chuck in the left hand side becomes actually velocity, which is called as ds by dt, and the chuck in the right hand side becomes the derivative of delta theta with respect to time, that is d theta by dt. And as we already know that ds by dt is called as velocity and d theta by dt is called as angular velocity, so we get that v is equal to r into omega, which is the relationship between linear speed and angular speed. And if we see the vector form of this, तो इस इक्वेशन का वेक्टर फॉर्म अगर हम देखना चाहते हैं तो वो भी देख सकते हैं आराम से. Relationship between the linear velocity v bar and angular velocity omega bar can be written like this: omega bar is equal to v bar is equal to omega bar cross r bar. And even in a diagram also we can see this, all these three quantities directed. So r bar is directed along the radius away from the center, v bar is directed along the tangent to the circle, and omega bar is directed outwards to the plane of the circle. Okay, so all these three are just perpendicular to each other. And remember that this uniform circular motion is an accelerated motion, just because the velocity at every point is going to be changing in direction. If we draw the velocity vectors at every point, then we can see clearly that the velocity vector is changing in direction at every point, and that's why the accelerated motion, uniform circular motion, is called as the accelerated motion. Remember, and you have to also find out the acceleration in this uniform circular motion soon. But just check your understanding first. Relationship between angular speed and linear speed, what is it? Just type in the chat box. Remember, the order is important, and also cross product is going to be there, not dot product, and vectors must be there. V bar equal to omega bar cross r bar. This C should be the correct option. Very good, Prashant. Uniform circular motion is an accelerated motion. Yes, it's true. The direction of velocity in uniform circular motion changes or remains constant. What can we say? यूनिफॉर्म सर्कुलर मोशन के अंदर जो डायरेक्शन होता है वेलोसिटी का, तो वो तो चेंज होता है, कंटिन्यूअसली चेंज होता है. वेरी गुड, चेंजिंग. यस. Now see here, uniform circular motion is a periodic motion, and that's why we can find out its time period and frequency also. So what do we mean by the period of circular motion? The time taken by the particle to complete one full revolution is called as the period of revolution. Okay, period of circular motion. जैसे फॉर एग्जांपल सेकेंड हैंड जो होता है क्लॉक का, तो यहाँ से सपोज वो स्टार्ट करता है तो ये पूरा कवर करके, पूरा सर्कल कंप्लीट करके वापस आने के लिए जो भी उसको टाइम लगता है तो उसको हम बोलेंगे पीरियड ऑफ सर्कुलर मोशन। ओके, इवन यहाँ पे भी ये पूरा सर्कल कंप्लीट करने के लिए जो टाइम लगेगा उसको हम बोल सकते हैं पीरियड ऑफ रिवॉल्यूशन। See here, the time taken by the particle performing UCM to complete one complete revolution is called as period of revolution. So if we consider the period can be written to be equal to circumference of the circle divided by speed, just because time is always equal to the distance upon speed. ये formula हमारे पास है already for uniform motion, so we can use it here and get that time के बदले क्या आएगा, period आएगा, और डिस्टेंस के बदले क्या आएगा, सर्कमफरेंस आएगा सर्कल का, और स्पीड तो स्पीड ही है, नो डाउट. So if you put all these values here, then we get the circumference replaced by 2 pi r, and that is to be divided by v here, so that we can get this period formula for period. But as we already proved that v is equal to r omega, so we can just use here and 2 pi r divided by r omega. So r gets cancelled, and what we are left with is 2 pi by omega as a formula for period here. And in the same way, we can find out the frequency of revolution. So the number of revolutions performed per unit time by the particle performing UCM is also called as the frequency of revolution. And it always is the reciprocal of the period, remember. So in time t, the particle completes one revolution. So what we can say is in 1 second, means one unit of time, it will complete 1 upon t revolutions. And that's why we can say that the frequency is going to be the reciprocal of time period. But as we know that this time period is equal to 2 pi by omega. So frequency का formula क्या होगा, omega by 2 pi. Remember, even frequency का और एक formula हम यहाँ पे लिख सकते हैं v by 2 pi r, जो कि 2 pi r upon v का उल्टा है, ठीक है, तो ये भी याद रखो अच्छी तरह से. And using this, we can also get the two formulae for omega. Omega will be 2 pi n. From this, if we take this 2 pi in that side, then we can get omega is equal to 2 pi n. And also omega can be written to be equal to 2 pi by t, correct है, because t itself is omega by 2 pi by omega. So omega के ये दो फॉर्मूले हमको मिल गए, याद रखो इनको ठीक से, they are important in MCQs. Okay, चलो next is just check your understanding. Number of revolutions performed per unit time in UCM is called as frequency, correct है, अभी हमने देखा. SI unit of frequency is per second और hertz both. ओके, पर सेकेंड भी बोल सकते हैं, या इवन उसको ऐसा सेकेंड इनवर्स भी लिख सकते हैं, या पर सेकेंड भी लिख सकते हैं, या हर्ट्ज भी लिख सकते हैं. ऑल ऑफ दिस मीन द सेम थिंग, नो डाउट, बट पर मिनट इज डिफरेंट. पर मिनट इज डिफरेंट. पीरियड ऑफ रिवॉल्यूशन इज गिवन बाय which formula? 2 pi r upon v, it's correct. 2 pi by omega is also correct. So A and B will be the correct one here. Yes. Now we will see the centripetal acceleration. What is the centripetal acceleration? See here, using calculus method, we can find out the expression for centripetal acceleration, because we know that the velocity is nothing but the rate of change of displacement, correct है? And the acceleration is nothing but the rate of change of velocity. So ये दोनों फॉर्मूले हमको यूज करने हैं यहाँ पे. So suppose that the particle is present at certain point P here. And suppose that particle moves from A to point P here. And suppose that points P is having the coordinates X and Y. Okay, X and Y उसके coordinates है. ये देखो ऐसे. तो उस केस में हम लिख सकते हैं यहाँ पे, ये X होगा, OM मतलब X होगा, और यहाँ पे ON मतलब क्या होगा, Y. Okay. तो इस केस में हम ये जो है इस वेक्टर APM को अगर थीटा बोल देते हैं, तो that theta will actually be omega t, just because we have that omega is equal to theta upon t, so t can be transferred that side so as to get this theta is equal to omega t. Okay, and radius vector at time t will be given by r bar, which is equal to x times of I bar and y times of j bar, according to the parallelogram law of vector addition. Okay, so we can get that from triangle POM, x can be expressed as r cos theta and y can be expressed as r sin theta, and theta is omega t, so we can get this theta replaced by omega t here. and theta also here also replaced by omega t, so that we can get x and y in terms of omega t. That is x equal to r cos omega t into I bar plus r sin omega t into j bar. Now, in order to find out the velocity, we have to just find out the derivative of this r bar. See here, if we just differentiate this equation of r bar with respect to time, then we can get the velocity. So according to the definition of velocity, v bar is given as d by dt of r bar, where r bar is already obtained to be r cos theta into I bar plus r sin theta into j bar. So r is a constant, can be taken out, and here we can see I bar is also constant, and derivative of cos omega t is only to be found out, and j bar is again a constant, and derivative of sin omega t is to be found out, which happens to be actually, देखो यहाँ पे cos omega t का डेरिवेटिव क्या बनता है, माइनस sin omega t, याद रखो ठीक से, into omega, remember, and also that the sin omega t का जो डेरिवेटिव है वो बनता है cos omega t multiple, it should be multiplied by omega according to the chain rule. So therefore we get this as a plus j bar into omega cos omega t, no doubt. And then we can just get this equation for velocity, which is actually going to be minus of r omega sin omega t into I bar plus r omega cos omega t into j bar. Okay, now just differentiate this equation once again so as to get the acceleration, because we know that acceleration itself is the derivative of velocity. So we can say that this derivative of velocity will be v bar यहाँ पे अगर रिप्लेस कर देते तो यहाँ पे I बार एंड r ओमेगा कांस्टेंट है, तो वो बाहर चले जाएंगे, और sin ओमेगा t का जो है वो डेरिवेटिव हमको निकालना पड़ेगा. तो अभी जैसा कि हम जानते हैं sin ओमेगा t का डेरिवेटिव क्या बनता है, cos ओमेगा t, और cos ओमेगा t का डेरिवेटिव बनता है minus sin ओमेगा t into omega obviously. So because of that we can get that, ये देखो sin ओमेगा t का डेरिवेटिव cos ओमेगा t, because of that this derivative of sin omega t will become omega cos omega t, and here cos omega t differentiates up to minus omega sin omega t. Therefore we can get this derivative of cos omega t as minus omega into sin omega t, and then we can just simplify this further and get this as minus I bar into r omega square cos omega t minus j bar r omega square sin omega t. If we take omega square minus omega square common, then what we are left in the side bracket, r bar r cos omega t I bar plus r sin omega t into j bar, and this is nothing but our r bar, and hence we can prove that acceleration a bar is actually going to be minus omega square into r bar, which is nothing but the formula for acceleration. Okay, this formula gives us that this negative sign shows that the direction of acceleration is going to be opposite to that of the this radius vector. तो रेडियस वेक्टर जिस भी डायरेक्शन में होगा उसके अपोजिट डायरेक्शन में एक्सेलरेशन वेक्टर होगा, बिल्कुल. एंड इन मैग्नीट्यूड वी कैन से द एक्सेलरेशन विल बी इक्वल टू ओमेगा स्क्वायर इनटू r, और वी कैन से इट विल बी v स्क्वायर अपॉन r, और वी कैन आल्सो कॉल इट एज a इज इक्वल टू v इनटू ओमेगा. ये भी उसका तीसरा फॉर्मूला है, याद रखो ठीक से. यस, let us see the next topics in the tomorrow's lecture. Okay.